from indicators, signs, and lighting mechanisms to data communications and other signaling, from machine vision systems to biological detection applications.
LEDs had been so useful that in anywhere you go, you can see its use and how helpful it has been to human living. You can see it on the streets, at home, or even our personal devices has it.
I am Gerald Doblado,
And I am Kim Howell delosReyes.
and we are going to dig into what is LED display technology.
All right, so the agenda of this topic is to discuss what is LED and move into the physics, explaining it. After that, we will move through the course of the discovery and milestones of LED. And lastly, we will going to see how LED is being used in modern technology. Light emitting diode is a semiconductor light source. It's a kind of solid state lighting where a semiconductor converts electricity to light without producing heat, usually in a small area of about 1 square millimeter or less. It's also a special type of diode or a specialized type of diode, as they are very similar electrical characteristics to a PN junction diode or a semiconductor device which has the electrical characteristic of passing current through itself in one direction only. It is also a combination of electrons from P and N types of semiconductors. To do this, holes from P-type semiconductors recombine with electrons from N-type semiconductors to produce lights. As compared to other incandescent light sources, LEDs are also low in power consumption, longer lifetime. It has improved physical robustness, smaller in sizes, and faster switching.
Now, let's go deeper to the physics in LEDs. So materials can be classified by their electric conductivity or the ability to carry electric current. On the molecular level, current is the rate of flow of electrons across the material, meaning a conducting material must have free electrons across to be able to conduct electricity. These electrons usually came from outermost shell of an atom or the valence band. For these electrons to escape its atom, energy is needed for them to be free. For a more technical term, the electron must jump from valence band to conduction band, and the amount of energy needed, illustrated by the band gap here, differentiates conductors, insulators, and semiconductors. For metals, the gap is virtually non-existent, and their utmost electrons can readily move into the presence of outside source like a battery. Insulators, on the other hand, have large band gaps, or we need large amount of energy just to push an electron out of the atom. Semiconductors stand between the two. It still has a band gap, but the energy needed to overcome this is not that large, and thermal energy is usually enough for most of the cases. Therefore, they can still conduct electricity, but not as large as the conductors. One remarkable end product of semiconductors is in the form of LEDs or light-emitting diodes. To better understand how LED emit light, let's take a look inside a diode. Okay. When an electron escapes its atom, it becomes one of the free electrons. Note that it leaves a hole or space from the atom's orbital where it came from. Other electrons with energies falling below the energy gap, remember the band gap, will occupy one of the holes in the valence band. The presence of these so-called holes is important to grasp how light is emitted by LEDs. Okay, let's go to the silicon. Silicon alone does not have enough electrons and holes for practical purposes. To note, silicon is a semiconductor example. To increase their numbers to construct a typical diode, one region is added with element such that there are more electrons in the region, and this is called the N-type region. The other region, on the other hand, is added with elements such that the region have more holes across. This is called the P-type region. When the two regions are combined without a voltage source, N-type's free electrons near the contact point diffuses through the p-type, then fill up the holes near the junction. As more and more electrons flow into the p-type region, it becomes more and more negatively charged, since electrons are negatively charged in nature, while the N-type region becomes more positive. If we have two regions with different charges, forces between the two regions will become present. This is Coulomb's law in principle. Those electrons with not enough energy to overcome this force cannot pass through the junction. This layer is called the depletion region. Therefore, at equilibrium, if no external voltage is present, the depletion region prevents further flow of electrons. If, in a case that enough voltage is applied between the diode, while the negative terminal is connected with the N region and the positive terminal is connected with the P region, electrons will be able to overcome the barrier. Upon crossing the barrier, some electrons with not enough energy to be free or stay within the conduction band will recombine with the holes in the P region. In the process, the electrons emit energy sometimes in the form of light as it goes to a lower energy region where holes are located. Note that not all semiconductors emit light. Some emit heat and is absorbed by the semiconductor itself. And that's how light is emitted by an LED. Looking to our typical LED, only a small part of it is actually the lighting element. Covering is to protect the semiconductor. Special semiconductors are used for LED applications like aluminum gallium indium phosphide to produce red, orange, and yellow LEDs, and indium gallium nitride for green, blue, and white LEDs.
So now let's proceed to the discovery and milestones of LEDs. In 1961, Robert Boyer and Gary Pittman invented an infrared light while working at Texas Instruments. Due to its microscopic size, it did not have practical everyday use.
The next year, in 1962, Nick Holonyak Jr. invented the first LED that produced visible red light while working at General Electric. He is dubbed as the father of the light-emitting diode.
While in 1972, M. George Crawford, while working at Monsanto, used one red and one green diode to create a pale yellow light. Crawford also invented an LED that was about 10 times brighter than Holonyak's. Monsanto became the first company to mass-produce LED lights.
In 1979, Shuji Nakamura, while working with Nishia, invented the ultra-bright blue LEDs that serve as the foundation for today's common commercial LEDs.
Blue light emitting diodes were common in the 1990s, which in turn led to the invention of white LEDs. These were created by scientists who applied the coating of phosphorus on the blue diodes to create a diffused white light. The technology was improved further by combining red, green, and blue diodes to create a white glow. This leap in innovation allowed for LEDs to be used in a variety of applications, from traffic lights, television sets, and flashlights, among others.
In 2000, the US Department of Energy pushes white LED lighting to spur their adoption as home lighting solutions.
And then in 2008, the Department of Energy announces the L-Prize competition, which was designed to encourage the development of super efficient solid-state lighting solutions and replace the inefficient incandescent bulbs.
In 2009, Philips submits its entry into the competition, a 60-watt incandescent equivalent that consumes just 10 watts of electricity.
So let's now proceed to LED in modern technology. One of the uses of LEDs is on signaling and communication. On the streets, we can see automobiles running light LEDs for signaling either turning left or right or a brake is being done. The use of brakes improves safety due to a great reduction in the time needed to light fully or faster rise time compared to an incandescent bulb.
With the development of high efficiency and high power LEDs, it has become possible to use LEDs in lighting and illumination. Efficient lighting is needed for sustainable architecture. As of 2011, some LED bulbs provide up to 150 lumens per watt, and even inexpensive low-end models typically exceed 50 lumens per watt, so that a 6-watt LED could achieve the same result as a standard 40-watt incandescent bulb.
Barcode scanners are the most common example of machine vision applications, and many of these scanners use red LEDs instead of lasers. Optical computer mice also use LEDs as a light source for the miniature camera within the mouse.
Now let's talk about LED display technology. LED display is one of the main screen displays that are being commercially used, as it is efficient, low energy consumption, which is especially needed for handhelds and chargeable devices, such as mobile phones and tablets. It is essentially a display consisting of many closed-space LEDs. By just varying the brightness of each LED, the diodes jointly form an image on the display.
So what are OLEDs? OLEDs stand for organic light emitting diodes. These are authotain self-emissive devices consisting of a multi-layer structure of organic materials between two electrodes, sandwiched between several charge transporting layers. The central emissive layer makes for the light emission. Companies like Samsung, LG, Sony, and Apple are some notable organizations using OLED display technology.
Over the last decade, one of the newest breakthroughs in developments in display technology is AMOLED, or active matrix organic light emitting diodes, a modified version of OLED. The main difference between AMOLED and OLED is that AMOLED display contains thin strips of thin film transistors behind each pixel. These transistors are like superhighways for electricity that help the electric current move more quickly across the entire display. In the presence of TFT, each pixel can be activated faster because of electricity can reach the pixels faster. And Samsung has developed their own AMOLED display, which they call as Super AMOLED, an AMOLED display with integrated touch function. Aside from Samsung, since 2019, major brands that uses AMOLED technology includes Apple, Huawei, Oppo, Vivo, and even Xiaomi.
MicroLED, also known as micro LED, MLED, or MULED, is an emerging flat panel display technology. MicroLED display consists of arrays of microscopic LEDs forming the individual pixel elements. Compared to widespread LCD technology, MicroLED displays offer better contrast, response times, and energy efficiency. Glow and Jasper Display Corporation demonstrated the world's first RGB microLED microdisplay, measuring around 0.55 inches or roughly 1.4 centimeters diagonally at SID Display Week last 2017. Some notable names which already uses microLEDs are Sony as crystal LED display, Samsung, and Apple, which has a secret production center for creating microLEDs.
So that wraps up our discussion with LEDs and LED display technology. Today, we have learned the physics behind how LED works.
We have also seen the breakthroughs and milestones since the discovery of LEDs until today.
We were able to appreciate its use in modern technology and among many uses of it on LED display technology.
And we have seen the different LED display technologies and how it evolved throughout the years. Again, this is Kim Howell delosReyes.
And Gerald Doblado, pleasant evening to everyone.